Hello everyone, I'm Akshay from Prodigy Educator, and today we'll be learning Maclaurin's series. Now Maclaurin series is a special case of Taylor series. The idea behind it is any function, say f of x, rather I should say any differentiable function can be written in this form of an infinite polynomial. Like I can write it as a naught plus a1 times x plus a2 times x square. Then I have plus a3 times x cube and so on. Like this, there are infinite terms in this. So our job is to find these coefficients a naught, a1, a2, a3, and so on. So let us derive a formula for this. Now to find a naught, what I'll do is I'll simply substitute x as 0. So if I substitute x as 0, in that case, all these terms will get vanished. So I can simply write a naught as f of 0. Cool. Now what I have to do is I have to find a1. In that case, what I'll do is I'll just differentiate this function. So I'll write f dash of x as, since a naught is a constant, it will simply get vanished. Here I'll write just 0 plus, here differentiation of a1 times x is simply a1 plus differentiation of this is 2a2 x plus differentiation of this term is 3a3 x square and so on, like this. Now I have to find a1, so I'll simply substitute x as 0 in this function. So I can write f dash of 0 as a1. So here it is, we got formula for a1, here it was for a0, then it was for a1. Now what I'll do is I'll differentiate this function again. So I have to simply write f double dash of x as 0 is anyway zeros, a1 is a constant, so its differentiation will be 0 as well. Now we will differentiate this term. So if I differentiate this term, I'll get 2 times a2 plus, now I'm differentiating this term. At that case, I'll get 3 times 2 times a3 into x cube. Now I think I should write a few more terms. In this only I'll write, so here I'll write a 4 times x raised to 4 plus I have a 5 times x raised to 5 plus and so on. So when I differentiate this function, I differentiated this function, so I got this. Now when I differentiate this function, I'll get 4 times a4, then x cube plus 5 times a5 x raised to 4 plus dot dot and so on. And then when I double differentiated it, at that case, I'll get, see, it was x square, sorry, this cube will go and I'll have x raised to 1 in this case. Perfect. Plus, when I differentiate this term, what I'll get? I'll get 4 times 3 times a4 x square plus when I differentiate this term, I'll get 5 times 4 times a raised to 5 x cube plus so on, many terms. Now you can see if I substitute x as 0 in this case, I'll write f double dash of 0. That will become 2 times a2 plus, since all these terms have a term of x, these will get vanished and simply these terms are equal to 0, 0, 0. So what I got a2 as, a2 I can write as f double dash of 0 upon 2. Perfect. We got a naught, a1, a2. Now I'll find a3. To find a3, I'll again differentiate this function. So in that case, I'll get f triple dash of x as, since this is a constant, it will get vanished. So we'll get a 0 here plus this term. I have to write 3 times 2 times 1 actually to show differentiation. Then we have a3 plus this function differentiating will get 4 times 3 times 2 times a4. Then I have x plus so on. Now I'll substitute x as 0 in this. So I'll get f triple dash of 0 as, in this case, this term will remain. So I can simply write this as 3 factorial. So you might guess a pattern in this. So this is 3 factorial a3 plus remaining all the terms have a term of x in this. So they all will get vanished. So I'll just simply write 0. So what I'm getting, I'm getting A3 as F triple dash of 0 upon 3 factorial. Similarly, A4 I'll get as A fourth dash of 0 upon 4 factorial, and A5 as a fifth dash, that is fifth time differentiation of 0 upon 5 factorial, and so on. So this is the pattern that we get. So overall, from this, we have derived the coefficients of the polynomial, and I can write any function as f of x. Now I'm writing the general expression as, first of all, a naught was, I'll just show you, a naught was f of 0, then a1 was f dash of 0, a2 was f double dash of 0 by 2. This 2 I can simply write as 2 factorial, just to show the pattern. And a3 was f triple dash of 0 by 3 factorial, and so on. So any function I'll write as, first of all, I'll write f of 0, which was a naught, plus I have to write x times f dash of 0. Just to show the pattern, I'll mention a 1 factorial here. Here I have to show 0 factorial. Now 0 factorial is anyways 1. 0 factorial is 1. Don't get confused. Plus I have to write x square by 2 factorial. Perfect. And then I will write f double dash of 0. Plus then I have x cube by 3 factorial into f triple dash of 0. Triple dash of 0. Plus x raised to 4 by 4 factorial times f fourth dash of 0, and so on. So this is the Maclaurin series. Any general sum, if I asked n term, nth term, or say n plus 1th term, so for that I'm simply writing here as x raised to n by n factorial times, we have to differentiate it n times, and so on. It is an infinite series. So this overall here is Maclaurin's series. Now what is the application? First of all, I'll derive the Maclaurin series of a sine function. We'll start with simple function. So I'll write sine function. So here I'll write f of x as, let f of x be sine x. F of x is sine x. So first of all, we need to find this f of 0, f dash of 0, f double dash of 0, f triple dash of 0, and so on. We'll find 3-4 terms in this. Okay, so I can write, first of all, I can simply write f of 0 as sine of 0. And you might know that sine of 0 is anyway 0. Then I have to differentiate it. So I'll write f dash of x. Sin x's differentiation is cos x. So cos x. So therefore, from this I can say f dash of 0 is cos of 0, which is 1. Then I have f double dash of x. That means we have to differentiate this function. Differentiation of cos x is minus sin x. Minus sin x implies f double dash of 0 is minus of sine 0. Now sine 0 is anyway 0, so no use of that minus sign. Then I'll write f triple dash of x. Triple dash of x. Differentiation of sine x is cos x, but since we have a minus sign here, so we'll get minus cos x. Minus cos x. From that I can write f triple dash of 0 is minus 1. As you know, cos 0 is 1 and we have a minus sign here. Then I'll differentiate it 4 times. That means 1 time more. The differentiation of cos x is minus sin x. That minus minus will make it plus. So I'll simply get sin x. So I have sin x. From that I can say f fourth dash of 0 is 0 anyways, and so on. So this is the procedure to find it. So from that I'll get sin x as, I'll write f of x as sin x. So first of all, f of 0 is anyway 0. So I have to write here 0. Plus, after that we have x by 1 factorial into f dash of x. Now f dash of 0, sorry. F dash of 0 is anyways 1. So from that I'll get simply 1 into x. Then after that I had 0. F double dash of 0. So here it's simply 0. Plus, then f triple dash of 0 was minus 1. So in that case, I'll get minus 1 then have x cube by 3 factorial, and then again I have a 0. And looking at pattern, we have this plus minus pattern, so I'll get plus x raised to 5 by 5 factorial, and so on. So if you see the pattern, this is the Maclaurin's series of sine function. So sine x is given by x, then I have minus x cube by 3 factorial, then I have plus x raised to 5 by 5 factorial, then I have minus x raised to 7 by 7 factorial, and so on. This series will continue on and on for infinite. Now, you might guess you know that sine function is an odd function. So see, all the odd terms are there. There is no even power. So well, that is a good verification of Maclaurin's series. Then I'll derive cos. Now I don't need to show the derivation of cos. I'll just simply write the derivation cos x. Now cos x is odd function, so you might guess the terms must be even in this case. So cos function we get 1 minus x square by 2 factorial. All the even terms you'll get, and this plus minus pattern goes on for cos as well. So I have plus x raised to 4 by 4 factorial. Then I have minus x raised to 6 by 6 factorial, and so on. Perfect. Now to show one simple thing, actually one simple yet a great formula of complex numbers, I'll derive Maclaurin's series for e raised to x as well. So let our function be f of x is e raised to x. Now you know that differentiation of e raised to x is anyways e raised to x. Again, if we differentiate it twice, we'll again get it as e raised to x, and so on. So f of 0 is equal to f dash of 0, which is again f double dash of 0, which is equal to all these coefficients. And you know f of 0, f double dash of 0, it is simply e raised to 0, which is 1. So all these coefficients for e raised to x are 1. So e raised to x is simply, I'll write e raised to x as 1 plus x square by 2 factorial plus x cube by 3 factorial plus x raised to 4 by 4 factorial plus x raised to 5 by 5 factorial plus, and so on. So this is the Taylor series expansion for e raised to x. Now you have to remember this, which is sin x and cos x. Actually, you have to remember Taylor series, or sorry, for Maclaurin series expansion for many standard functions, the trigonometric functions, and there are some algebraic functions as well. In fact, the binomial theorem for integral n is derived like this, by this method. Now, what I'll do is, I'll simply substitute x as I theta. Now, you might be knowing that I'm deriving which formula. I'm basically deriving e raised to I theta formula, which is cos theta plus I sin theta, as you might have guessed. So in this function, I have to simply substitute x as I theta. So e raised to I theta must be, this is LHS by the way, LHS for this formula. E raised to I theta is given by, now wherever there is x, I have to simply substitute I theta. So 1 plus, instead of x I'm substituting I theta, plus I theta square by 2 factorial plus I theta cube by 3 factorial plus I theta raised to 4 by 4 factorial plus I theta raised to 5 by 5 factorial plus, and so on. Now I is nothing but root of minus 1, that you must know, which we learned in complex numbers. So 1 plus, I'll write I times theta plus, now I square, since I is root of minus 1, so I square is minus 1. So this will become minus of theta square by 2 factorial. Then I have I cube. I cube can be written as I square times I. Now I square is minus 1, so I cube becomes minus I. I'll just simply write here I cube. So I cube is minus I. So instead of this, I'll write minus I times theta cube by 3 factorial. Then I have I raised to 4. Now I raised to 4 is I square times I square, which is minus 1 times minus 1, minus 1 times minus 1, which is again 1. So in that case, I'll get a plus 1. So that is plus theta raised to 4 by 4 factorial. Again, I raised to 5. I raised to 5 can be written as I raised to 4 times I. I raised to 4 is 1. So this is simply plus I times theta raised to 5 by 5 factorial and so on. Now what I'll do is I'll separate the real part and imaginary part. Now real part are those parts, those terms in which there is no term of I, like this term, then I have this term. And imaginary part are those parts in which we have a term of I, this part, this part, this part. Perfect. So e raised to I theta can be written as, first of all, I'll write here 1, then I'll write minus theta square by 2 factorial, then I have plus theta raised to 4 by 4 factorial, and so on. Plus, for this imaginary part, I'll just simply take I as common. So I times I have theta, then I have this term, which is minus theta cube by 3 factorial. Then I have plus theta raised to 5 by 5 factorial. Now we are getting something which we saw just few minutes earlier, that e raised to I theta is this term. This term, if you might have guessed, this term is nothing but expansion of sine theta. If I substitute x as theta here, we'll get theta minus theta cube by 3 factorial plus theta raised to 5 by 5 factorial, which is this term. All right. And this term is simply cos theta. So from this we get formula cos theta plus I sine theta. Now this is one of my favorite mathematical formula. In fact, not only mine, great mathematician Carl Friedrich Gauss, his favorite formula as well. This is known as Euler's identity. Very great, very useful formula. It has tons of applications, and I'll be making videos on applications of this formula, really. So this formula, then we have sine formula, e raised to x, cos x, and many more. This was derived from a simple idea that any function, or I'll say any differentiable function, can be written as a series of infinite polynomial. And then we derived the coefficients, and then we wrote the general formula. I'll just simply box this general formula here. We have, just memorize it, guys. It is a very important and very useful formula, this formula. Okay, fine. And then we derived, we use this formula for deriving the series of sin x, cos x, e raised to x, and from that we arrived at the derivation of this great formula, which is e raised to I theta as cos theta plus I sin theta. Well, I hope you guys enjoyed this video. I'm soon going to make lots and lots of videos, and one of my favorite topics, which is complex numbers, and whose master formula is this formula, a raised to I theta formula. Thank you everyone for watching. If you like this video, give it a thumbs up, share this, comment, and also for more such videos, you can join Prodigy Educare. You'll get this many of these videos. So thank you everyone for watching.